These notes are going to cover the unit circle. On the unit circle, we have a radius of 1, and what I'd like to first review is what would the lengths of our sides of our triangles be if our radius was 1. So quick review on a 30, 60, 90, if the hypotenuse is equal to 1, then that means that our short leg is equal to a half, because this is half the length of the hypotenuse, and the long leg becomes radical 3 times that short leg, which becomes root 3 over 2. On the 30, 60, 90 here in orange, it is just rotated. So now 1 still being the hypotenuse means now the vertical side is a half, and our long leg over here is root 3 over 2. On the next 45, 45, 90, to get to the leg from your hypotenuse, we have to divide by root 2. And taking 1 dividing by root 2, you end up with a length of root 2 over 2 for both legs, since it is an isosceles triangle. Using those ratios, we're actually going to incorporate what the values on the unit circle would be for the 45, 45, 90 triangle. Moving down to our circle here, we have in quadrant 1, a yellow 45, 45 degree 90 triangle. And since it's a unit circle, our radius is equal to 1, which makes the length of our vertical piece radical 2 over 2, and our horizontal piece over here radical 2 over 2. With those two lengths, we can then find the corresponding coordinate for this point up here on, this point on our unit circle, which would correspond to be radical 2 over 2 for x and radical 2 over 2 for y. This is for a 45 degree angle in degrees, and of course in radians, we know that that is equal to pi over 4. As we rotate, just as a quick review, in degrees, this angle up here is 90 degrees at our positive y-axis, and in radians, it is pi over 2. Okay, moving on to quadrant 2. We can take this triangle in quadrant 2 and now have a reference angle, which here is 45 degrees. We are actually going to take this triangle, and I'm going to do this once. We're going to flip it and move it over here. So now this reference angle here is now 45 degrees. Well, what angle actually corresponds with that 45 degrees will be 135 degrees in radians. In degrees. In terms of radians, that is 3 pi over 4 radians. Well, what would this coordinate be? Now we're in quadrant 2. Our hypotenuse is still 1. The lengths of the sides have not changed. So our vertical piece still has a length of root 2 over 2. And our horizontal piece also has a length of root 2 over 2. But what has changed is the direction is now negative for our x value. And negative is for direction, not for length. So our coordinate becomes negative root 2 over 2 and positive root 2 over 2 for y. As we continue to rotate in on our unit circle, out here is going to be 180 degrees, which we all know is pi radians. Taking this triangle, and if you can imagine taking this triangle and flipping it over the x-axis, our 45 degree reference angle is now going to be down here. So what corresponds now? I can draw in. I don't have a fancy triangle. You could certainly draw in what it would be. And this vertical length right here is root 2 over 2. But again, we're in quadrant 3, gone negative. So it will be negative root 2 over 2. So our corresponding coordinate here, negative root 2 over 2 for x, negative root 2 over 2 for y. That didn't come out right. What is that angle? Well, we've gone 180. In degrees, we've gone 180, and a reference angle of 45 degrees more brings us to an angle of 225 degrees. In terms of radians, we've gone pi over 4 more than the pi, so that becomes 5 pi over 4. As we continue on, whoops, sorry. As we continue on around this unit circle, down here, our angle in degrees is 270, and in radians, this is 3 pi over 2. Our final coordinate, our final 45-degree reference angle here in quadrant 4, this is now 45 degrees as a reference angle. We can draw in the triangle if it helps you, and see that this vertical piece is still root 2 over 2, but since it's quadrant 4, it's gone in the negative direction. And so in quadrant 4, we have a positive x value of root 2 over 2, and then a negative y value of negative root 2 over 2. Rotating around in degrees, this corresponding angle, right, 360 minus our 45 is 315 degrees. In radians, that becomes 7 pi over 4 radians. Okay. Back to our positive x-axis, we know we have 0 degrees, 0 radians, or 360 degrees, and 2 pi radians. Okay. So there's your 45 degree reference angles in all of your quadrants on the unit circle. Moving on to our second circle, we now have our 30, 60, 90 degree reference angles that we want to look at what those coordinates would actually be. Well, taking our values for the 30, 60, 90 of the triangle we had in the beginning, our vertical x piece with a hypotenuse of 1 because it is on the unit circle. This vertical piece is now a half, and then the horizontal piece is radical 3 over 2. So the coordinate that corresponds to this 30-degree angle is we've gone over radical 3 over 2 in the x direction and 1 over 2 up in the y direction. This, of course, is a 30-degree angle, and in terms of radians, that angle is pi over 6. Let's take this reference angle of 30 degrees and put it in our quadrant 2. We're going to flip it over, and let's look where this falls. This 30-degree angle is now in here, and our corresponding coordinate is up here. So our sides, the 1/2 vertical hasn't changed. We're going across the x-axis as we did with the 45, 90. It is now the negative direction. So our coordinate that corresponds is negative 3 over 2 and positive 1/2. What is the angle in quadrant 2 that generates a 30-degree reference angle? That is 150 degrees. And in radians, that angle is equivalent to 5 pi over 6. Okay. Quickly moving on to quadrant 3, we can draw in that triangle. There's 30. Can we figure this out without labeling the rest of the parts? I sure hope so, but I'm going to label it anyway. This is negative 1/2. So in the x direction, we've gone negative root 3 over 2, and then in the y direction, negative 1/2. Our angle in degrees, we've gone 180 plus 30 more, which is for a total of 240 degrees. In radians, we've gone pi plus pi over 6, which is then 7 pi over 6 for radians. Last but not least, quadrant 4. I'm just going to put in a 30-degree angle here. What do we have for our coordinate? Well, we've gone over in the x direction, root 3 over 2, and in the y direction, we've gone down negative 1/2. In quadrant 3, this angle is 360 minus 30, which gives us 330 degrees. And then in terms of radians, this becomes 11 pi over 6. All of the angles and coordinates that we've just covered with the 45, 45, 90 and the 30, 60, 90 are imperative for you to memorize and know. These are not things you're going to have to redraw every time. You do need to memorize these. Okay, looking at this though, and the 45, 45, 90, can we start to see some type of pattern? And the answer is yes. So if we look at quadrant 1, N2, N3, N4, what do you notice about all those coordinates is that they are the same in value. What's different is the positive and negatives, and those are based on direction. So once you have your reference angle, you know your reference triangle based on where you are, quadrant 1, 2, 3, or 4, you can then determine, well, which pieces are positive or negative. So in essence, you really just need to know quadrant 1. And then once you know quadrant 1, you can generate the next 3 coordinates very easily. And that's what we are going to practice doing with our final ratios for our 30, 60, 90 that has given us a 60-degree reference angle. So our 60-degree reference angle is here. I am going to label, just for this one, that our short leg here is now on x. This is a half. And our vertical piece is root 3 over 2. So our coordinate is 1/2 and then root 3 over 2. This is for a 60-degree angle or a pi over 3 radian degree angle. Moving into quadrant 2, not drawing a triangle, but I will label out where the 60-degree reference angle is. If our coordinate is 1/2 root 3 over 2, it is the same in quadrant 2. However, because we've gone in the negative x direction, our negative will be on the x of 1/2, and our y value, root 3 over 2, will remain for the y. Moving on to, and our angles. Our angle in quadrant 2 will be 120 degrees. And in terms of radians, that angle will be 2 pi over 3. And rotating down into quadrant 3, let's draw in this reference angle here, 60 degrees, but I'm not going to draw in the reference triangle this time, just like before. What do we get for our coordinate? Well, again, we've gone negative x and we're going negative y. So we're taking the coordinate in quadrant 1 and we're making both x and y now negative. So this becomes negative 1/2 negative root 3 over 2. The angle in degrees that corresponds with a 60-degree reference angle is 240 degrees. And in radians, that angle is 4 pi over 3. And last but not least, our 60-degree reference angle in quadrant 4 has gone over positive 1/2 in the x direction and will be going negative for y, so negative root 3 over 2 for our y value. In degrees in quadrant 4, this is 300 degrees, and that angle in radians will be 5 pi over 4. Nope, sorry, 3. I don't know where that came from, sorry. 5 pi over 3. All 3 of those triangles and all of those coordinates and corresponding angles are a must to memorize. On your next page of notes, quick decimal values in your calculator to look at. You should know how to make a fraction, put in a radical into that fraction, and just for reference, this first one is 0.866. We are going to round to 3 decimal places, right? That's your nearest thousandth place. Your root 3 over 3 is 0.577, and root 2 over 2, 0.707, and root 3 is equivalent to 1.73. Okay, why are they there? Because I want to show you what happens, or what your sine, cosine, tangent are equivalent to, and those numbers certainly help. If you go back to your quadrant 1 reference angles for your 30 degrees, and we look at this sine ratio for 30. Since our hypotenuse is equal to 1, our sine ratio is just equal to the half that is your y value, right? Because it's 1/2 over 1. This, of course, we know is 0.5. For our 30-degree angle, that is our x value over y, so it's √3 over 2. And as we did the decimal before, 0.866. And to finish this up, tangent, opposite over adjacent, you will have to do a little bit of algebra, but it comes out reduced to be √3 over 3 with a decimal value of 0.577. Problem with that algebra, please come see me. For your 60-degree angle, if you look at the 60-degree reference angle in quadrant 1, you will see that the equivalent value is radical 3. Is equivalent to the square root of 3 over 2, which has a decimal value of 0.866. For a cosine of 60, it is equivalent to 1/2, which is 0.5. And to finish this up, this becomes radical 3, which is 1.73. When you look closely at those two columns, and what do you notice? Hopefully you're noticing that the sine of 30 and the cosine of 60 are the same, and the cosine of 30 and the sine of 60 are the same ratio equivalent. And that is not a coincidence. Those functions are called cofunctions, and they do have a relationship, 30 and 60. They're coterminal angles. So your sine and your cosine ratios will have reversed values for coterminal angles. That's why they're called cofunctions. All right, moving down to the 45-degree angles. This is actually the nicest one. It's an isosceles triangle. We end up with √2 over 2 for the value of the sine of 45, which is 0.707. Since it's isosceles, our adjacent and opposite are the same, so the same ratios. And then finally, anything over itself, which will happen for x and y, tangent is equal to 1, which is equal to 1. All right, very, very important we know. Not necessarily the decimal values, but absolutely those ratios and fractions you do need to be familiar with. Okay, so our unit circle, if we look at what's to the right, we know on this unit circle that we have an x value, y value. We're going to make our radius on the unit circle always equal to 1. Well, if that's the case, what is this particular coordinate for x and for y every single time? And you can go back to look at this. This has a value of 1, 0. This has a value of 0, 1. Well, what happens when you go over x over 1? That ratio for that angle is always going to be equal to cosine. What is the y value always equal to on the unit circle? It is always equal to the sine of theta. So that coordinate is equivalent to cosine theta, sine theta on the unit circle. So that's relevant over here. So when we look at the sine of theta and you're on the unit circle, it will always, always, always equal whatever your y coordinate is. For cosine, it will always equal whatever your x coordinate is. Well, what will tangent equal? Tangent is equal to still y over x, always opposite over adjacent, or sine over cosine. Cosecant, what do we know about cosecant? It is the reciprocal to sine, so it is equal to 1 over y. Secant's reciprocal to cosine, 1 over x, and cotangent, the reciprocal of tangent, and it'll be 1 over y. Okay. Those values, very, very important. They are only apply to the unit circle. When you have that written down, let's go to our last page and look at our quadrantal angles. Quadrantal angles are angles that fall on the positive or negative x-axis or the positive and negative y value x-axis. So you have 0, 90, 180, or 270. Just to, so I don't have to flip back and forth, reference, when you have 0 degrees, this is equivalent to the coordinate on the unit circle as 1, 0. If we rotate up to 90, this coordinate is 0, 1 on the unit circle. Keep rotating to 180. This coordinate becomes negative 1, 0, and sine of 270 on your unit circle falls at the point of 0, negative 1. That's important. Why is that important? Because there are your x and y values. What do we know sine is equal to? Well, as we just saw on the page before, sine is equal to y. What was cosine equal to? X. What was tangent equal to? Y over x. So in every one of these coordinates, here's your x and here's your y. So equivalent values for a sine of 0, without doing any calculation, it is equal to 0. That is your y value. Your cosine value is equal to its x value of 1, and tangent is going to be y over x. We'll put a 0 over 1, and that is equal to 0. For the sine of 90, again, looking at what y is equal to 1. Cosine x is equal to 0. Tangent y over x. What happens this time? We end up with 0 in the denominator. What do we write? We write undefined. It is an undefined value. Okay, sine of 180. Sine of 180, that's your y value, that is 0. Cosine is now negative 1, that's your x. And 0 over negative 1, that is equal to 0. Moving on, last but not least, to 270. Sine is equal to our y, which is negative 1. Cosine is equal to x, which is 0. And again, negative 1 over 0 will be undefined. Those quadrantal values you also need to be very familiar with and know them by heart. Okay, we have quotient identities. What's a quotient identity? Well, it's basically a quotient is a fraction. So what fraction is tangent? Yes, it is y over x, but what is y equivalent to again? Y is equivalent to sine. So if your quotient identity or tangent is equal to y over x, we know y as being sine of theta. So therefore, x being cosine of theta creates that fraction, sine of theta over cosine theta. In a similar way, cotangent, which is the reciprocal, now becomes x over y, and we end up with cosine theta over sine theta. Very, very important. When we have values of x and y, we can write them also for tangent and cotangent in a similar way. Okay, so our Pythagorean identity for this last one. Well, what's Pythagorean? You hear the word Pythagorean, what do you think of? You think of the Pythagorean theorem. Pythagorean theorem applies to all right triangles. And on our unit circle, we have all of these right triangles. What are they? Based on x, based on y, and of course, based on our radius. So our Pythagorean theorem tells us that x squared plus y squared is equal to r squared, right? True for every single right triangle. But from our unit circle, what do we know? We know that x is equal to the cosine of theta, and we know y is equal to sine of theta. And we also know that r is equal to 1. That's what we know from our unit circle. Because of those things, we can do a little bit of substitution and rewrite our Pythagorean theorem in terms of sine and cosine. So if we take and now substitute for for x, we're going to put in cosine theta, right? For y, we are going to put in sine theta, and we're going to square that. For r, where we're putting in r to square, that is a value of 1. While simplifying this, how you write a cosine squared, or sine squared, notation-wise, it looks like this. It comes out to be cosine, and you write the square before the angle. That means cosine squared theta. In a similar way, we're going to write it out for sine, and of course, we know 1 squared is 1. This is one of the most used and most popular identities in trig. Don't forget, that's one of the three different Pythagorean identities that you have. Okay, that concludes these notes for today, and now you can continue on to the homework worksheet.